Pleasure to introduce Praneeth Netrapalli from Microsoft Research Bangalore. He is known for his work in non-convex optimization and global guarantees for machine learning.
Thanks, Hari, and thanks to all the organizers for inviting me, and thank you all for coming. So today I'll be talking about smooth analysis for obtaining low-rank solutions to semi-definite programs, and this is joint work with Srinath Bhojanapalli at Google, Nicola Bhumal at Princeton, and Prateek Jain also at Microsoft Research in India. Okay. So the subject of the talk is on solving semi-definite programs. What are semi-definite programs, or SDPs for short? They are optimization problems where we have a iterate X, which is a n cross n matrix, and we wish to minimize a linear form. So the inner product of C comma X subject to linear constraints AIX equal to BI, with the additional important constraint that X be a positive semi-definite matrix, meaning that X is a symmetric matrix and all the eigenvalues of X are non-negative. Okay. Semi-definite programs have several applications. Some of the most prominent ones include clustering in the machine learning community. There are a lot of problems in control theory which can be posed as semi-definite programs, and in the theoretical computer science literature there are a lot of important problems for which the best known algorithms are by solving semi-definite programs. Okay, and because semi-definite programs have a lot of applicability, there has been a lot of work on developing efficient algorithms for solving semi-definite programs. And some of the most prominent examples include interior point methods, ellipsoid method, multiplicative weight update method, and so on. While all of these are polynomial time algorithms, they still do not scale to very large data sizes, and the motivated by this problem of scaling, of being able to solve semi-definite programs on really large data sizes, Burer and Monteiro in 2003 came up with a new approach which is much faster, and empirically they demonstrated that on several problems, standard problems like maxcut and so on, their approach, they have shown it to work very well empirically. And they also provide a lot of interesting theoretical results about their algorithm, but eventually they stop short of being able to prove the correctness of their algorithm in general. Okay, so the algorithm has very good empirical performance, but its correctness is not really known in general. And a one-line summary of the work that I'm talking about here is to make progress on the situation and show that a simple variant of the Burer-Monteiro approach actually gets the right answer in solving semi-definite programs in a particular sense. So I'll talk about it in more detail. Okay. So that's the background of the talk. So let me now start by introducing what exactly is the Burer-Monteiro approach for solving the semi-definite program. Okay. The basic building block of the Burer-Monteiro approach is this interesting result by Barvinok and by Pataki, which says that take any feasible semi-definite program, it has at least one solution whose rank is at most about square root of m. Here m is the number of constraints. So we see here m is the number of constraints, n is the dimension of the matrix, and what this result says, this is an existential result. This says that any semi-definite program which is feasible has at least one solution which is of rank about square root of m. In most practical applications, we usually have m, which is the number of constraints, to be of the same order as the dimension of the matrix n. So what this says is that any semi-definite program of this sort actually has a solution of rank about square root n. Okay. A priori, it's not clear why there should exist a solution of rank even n minus 1, but this is indeed saying that you actually have solutions of rank square root n. Okay. So that's why this is kind of surprising and very interesting result. And the Burer-Monteiro approach tries to make use of this existential result to actually design a faster algorithm. And the way they try to do it is by directly operating in the low rank space where you are dealing with a lower dimensional object, and hopefully the iterations in this can be much faster than the higher dimensional space. And so the algorithm, if we can make it work in this low rank space, hopefully we'll get the solution much faster than operating in the higher dimensional space. Okay, yeah. So we have these constraints, right? Okay. So the constraints have to be feasible. Yeah, that's all. Yeah. Yeah. any extreme point actually has this property, and there is at least one extreme point which is a optimum. So that's why there is this existential property. Yeah. Okay. So more concretely, what the Burer-Monteiro approach tries to do is, given an SDP of the form on the left there, minimize Cx subject to Aix equal to Bi and x greater than or equal to 0. We replace X, which is an n cross n matrix, with UU transpose, where U is only an n cross k matrix. Okay. So we want to minimize C UU transpose subject to AI UU transpose equal to Bi, and the positive semi-definite constraint is no longer required here, because by the reparameterization it automatically is a positive semi-definite matrix, and we wish to solve this new constraint problem. And as I mentioned, the main advantage is that we are reducing the ambient dimension from n square to nk, where k is actually much smaller than n. Okay. Now, how do we solve this constraint optimization problem? One of the simplest ways, at least conceptually, of solving a constraint optimization problem is using the penalty formulation, where we choose a penalty parameter mu that we have here, and we write an unconstrained optimization problem which includes both the objective plus the penalty parameter times a square on how much we are violating the constraints by. Okay. And if we choose mu large enough, then we want to we are penalizing the violation of constraints more and more. So for mu large enough, we will get an approximately feasible solution. Now I should point out that the penalty formulation is not the best way to solve a constraint optimization problem or transform a constraint optimization problem into an unconstrained optimization problem. There are much better ways, more sophisticated ways, such as augmented Lagrangian method and so on. And the original Burer-Monteiro approach does indeed use augmented Lagrangian. But for the purposes of this work, we'll just work with the penalty formulation. I'll say a bit more about augmented Lagrangian methods towards the end of this talk. Okay. For the purposes of this talk, I'll just be focusing on the penalty formulation of this problem. Okay. Yeah, I'm assuming that I'm just working with this. Yeah. 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 So the biggest challenge about solving this problem is that it's actually not a convex problem. Even here, it's not a convex problem, and even this unconstrained problem is not a convex problem. So in general, we cannot really get to global optima in polynomial time or even to local optima. But then there has been a lot of work in non-convex optimization recently. And what exactly can we do for general non-convex problems? Yeah. You can verify, like you can write down the Hessian, and it has both a positive term and a negative term. So you can find points where the Hessian is not positive semi-definite. Yeah. Okay. So for general non-convex problems, what is it that we can do efficiently? In general, we can find stationary points efficiently, and within stationary points, there are different levels of stationary points. First order stationary points are those where the gradient is equal to 0, and an approximate notion of first order stationary point is that the norm of the gradient is at most epsilon. Okay. And similarly, there is a notion of second order stationary point where the gradient is equal to 0 and the Hessian is positive semi-definite. The approximate versions of this is again that the norm of the gradient is less than or equal to some epsilon 1, and the smallest eigenvalue of the Hessian is at most is greater than or equal to minus epsilon 2. Okay. And there has been a lot of recent work on finding second order stationary points efficiently, even for large scale problems. And if we apply those methods to this particular problem, we can find these second order stationary points. We should also note that the second order stationary point, first order stationarity and second order stationarity, these are necessary conditions for optimality but not sufficient. So in general, these are not sufficient to guarantee any kind of global optimality or even local optimality. But for the particular problem that we are interested in, because it's of a very special nature, we might wonder whether second order stationary points have any nice structure for the problem that we are interested in. Okay. In a recent work, very interesting work by Bumal et al., they actually indeed show that for the problem that we are considering, which is here, it turns out that once k is greater than or equal to about square root of m, for almost all C is the objective matrix here C, for almost all C, every second order stationary point is a global optimum. Okay. More concretely, what this means is that let's say we fix AI and BI, right? And then for every C, we will ask whether there exists a spurious second order stationary point, meaning that is there a second order stationary point which is not a global optimum? And if there is, then we call that C a bad phi. And if we consider the set of all the bad phis, what this paper shows is that it has Lebesgue measure 0. So if we pick a C at random, then with probability 1, if we pick a C at random with probability 1, every second order stationary point is a global optimum. So we can then use the local algorithms which can find the second order stationary points, and then this result tells us that any second order stationary point is indeed a global optimum. Okay, that's the usefulness of this result. But then this leaves two questions open. So the first one is whether this almost all, is it required or not? As a proof, they are able to show only almost all, but they don't really exhibit whether this C is not empty or maybe it's empty. So they don't answer that question. So that's the first question. And the second question is they show only for exact second order stationary points are exact global optima. But when we are running algorithms in practice, we can never really find exact second order stationary points, but we can only find approximate second order stationary points. So from a computational point of view, the more interesting question is whether approximate second order stationary points are approximate global optima. Okay, and these are the two questions that we consider. And sorry, there could be spurious first. So in most of these cases, like 0 will be a first order stationary point. If you take BIs to be 0, then 0. No, so the measure is only over C. Yeah, because when you are running an optimization algorithm, you will eventually converge only to optima, right? So there could be some measures of things, but yeah. Okay, so these are the two questions that we consider, and we answer both of them in the affirmative. So firstly, we provide an example of a problem where there is a C for which there exists a spurious second order stationary point. So the almost all in the statement is necessary. This is not true for every C. Okay, that's the first result. And the second one is that we show that approximate second order stationary points are approximate global optima for perturbed SDPs. So second order stationary point, the approximation is in what is the norm of the gradient and what is the smallest eigenvalue of the Hessian, right? And this approximate here is approximate in terms of the objective value of this thing. Yeah, yeah. And you can transfer like how approximate you are here to how approximate you are here. Okay. So let me be a bit more concrete about this second statement. So when I say perturb, we look at the problem in the smooth analysis sense. What I mean by that is we are given a problem which has the parameter C, the matrix C, the matrices AI, and then the scalars BI, right? We consider the same problem with the same AI and BI, but then C is actually perturbed additively by a random Gaussian matrix G. So we have C plus G, where G is a random Gaussian symmetric matrix with each entry of standard deviation epsilon. Okay. So instead of considering just C, we look at C plus G and then consider the modified problem that we have here. For problems of this sort, we show that with high probability, once the inner dimension K that we are optimizing on is taken to be about square root of m log 1 over epsilon, every epsilon second order stationary point is an epsilon global optimum. Okay. So with high probability in terms of the randomness in G, and this high probability is exponential in the dimension. Yeah. Okay. So this is the main result. Is in a low dimensional manifold. Low dimensional manifold. But when you go to like the manifold could have been something like this, which when you expand by epsilon could pretty much occupy the entire space. What our result shows is that that does not happen. Yeah, of the perturbed. So yeah, so both of them are also kind of close because G itself is not too large because you are taking G to be also epsilon. but we haven't carefully done that computation. Yeah, but they will not be very far apart. Yeah. Yeah. So there may be other polynomial in dimension factors when I go from here to here, because G itself, each entry is epsilon, but it is a D cross D matrix. So there could be some factor of D when you go from here to here. As n cross n, sorry. Yeah. There is no D. N is the dimension. Yeah. For the analysis that we currently have, it is required, and I'll come to exactly why it is required. Intuitively, I would think it's not required, but I think from a random matrix theory point of view, we know much more about Gaussians than other random matrices. But I'll come to that point a little later on during my talk. Okay. So in the rest of this talk, let me just spend time on giving you the main ideas of the proof. Okay, so there are two key steps in the entire argument, and both of these have been developed in previous work by others. So the first one is that, okay, so the main setting is that we have a function f which is convex, but then we are looking at f of u transpose, and it's not convex in u. Okay. So the two key steps. So the first key step is that if you have any second order stationary point which is rank deficient, meaning that its smallest singular value is equal to 0, then it is a global optimum. So this was established in the original paper by Burer and Monteiro. If u is a second order stationary point and the smallest singular value of u, because u is n cross k, sigma k is the smallest, which is also kth largest singular value of u. If it is equal to 0, then u is a global optimum. And the second one is that for perturbed SDPs, when we add this Gaussian noise or whatever, with probability 1, if the inner dimension k is actually large enough, about square root m, then all first order stationary points have smallest singular value equal to 0. So the main idea is that you take a second order stationary point, you know that second order stationary points are also first order stationary points. So by the second point, we know that they have sigma k of u equal to 0. And then you plug that in here, it means that u is a global optimum. So this basically says why all second order stationary points are global optima. Okay. And our work here is to make all of this robust, meaning that if I have an approximate second order stationary point and sigma k of u is small, then u is an approximate global optimum. And similarly for perturbed SDPs with high probability, if k is greater than square root of m log 1 or epsilon, all approximate first order stationary points have small sigma k of u. So the main work that we have to do is take whatever steps have been established previously and make them robust, so that we actually can say something about approximate second order stationary points rather than exact second order stationary points. So I'll first talk about the second part, and then I'll briefly talk about the first part. So the second part is that all approximate first order stationary points have smallest singular value. Okay. So let's recall the function that we are trying to optimize. So this is the function that we are trying to optimize, and what we mean by an approximate first order stationary point is that the norm of the gradient is small, and the quantity inside the norm here is the gradient. It looks pretty complicated, but the high level picture I want you to get is that it can be written as the product of two matrices. So the first matrix is this complicated thing, and the second matrix is just the iterate u. So this complicated matrix times u is the gradient, and because it's an approximate first order stationary point, this matrix is pretty small. Yeah, so not the condition number. No, I'm not assuming anything about the condition. I'm only assuming everything is an upper bound on everything, like the norm of C, norm of A, and so on, but nothing on the lowest singular value. The Gaussian will automatically give me, so I don't need anything from C is what I'm saying. Yeah. Yeah. Okay, so there are, from an optimization point of view, there are two kind of results. So one is where you depend on the condition number and then you get a geometric convergence, but you don't have to depend on the condition number. You can also get things which only depend on upper bounds like smoothness and so on, but then you don't get geometric convergence, but you still get convergence even in that setting. Okay, so by first order stationary point, approximate first order stationary point, we know that the product of these two matrices is small. And as an aside, so if we denote this more complicated matrix by H, so we have H times U, right? And as an aside, we can write this lower bound on product of matrices, which is simple and is very well known, and is also not very difficult to show by using the variational characterization of singular values, that the norm of the product of two matrices is lower bounded by the product of n minus k plus 1 singular value of H and the k singular value of U. Okay, this is very closely related to Weyls inequalities on the eigenvalues of products of matrices and so on. Once you have this, and if we recall, what we want to show is that sigma k of U is small, right? And this is precisely in the right direction. So we can show that, we can argue that sigma k of U is less than or equal to the norm of HU divided by sigma n minus k plus 1 of H. Okay. By first order stationarity, we already saw that this is small. So by first order stationarity, we already saw that the norm of the product is less than or equal to epsilon, and all we need to show is that this thing in the denominator here is large. So we need to show a lower bound on this quantity, and then we'll have an upper bound on sigma k of U. Okay, so what is this thing that we want to show a lower bound on? So it has some fixed matrices plus random Gaussian matrix G, right? Now let's first look at what happens if we just had the random Gaussian matrix without any of these additional terms, and then we'll come to the additional terms. If sigma I of G denotes the ith singular value of G, it is easy to show that the smallest singular value of G, sigma n of G, the probability that it's equal to 0 is equal to 0. With probability 1, a random Gaussian matrix is invertible. We can in fact actually say much more. In general, the n minus kth singular value of G is of the order of k over square root n. Okay, and we can also actually obtain large deviation bounds on these singular values. In particular, the probability that sigma n minus k of G is smaller than some small constant C times k over square root n. So k over square root n times some other constant is the usual value, and the probability that this is much smaller by constant factor smaller than its typical value goes down actually exponentially in k square. Okay, and we can also extend the same result for from G to G plus A for any fixed matrix A, and there is no dependence on the matrix A. A could be any arbitrary matrix, and this result still holds true where G is replaced by G plus A. Yeah. Sorry? Yeah, so I wrote a little c and a capital C here, they are different. I mean, this capital C depends on little c, but usually choose some small constant here and then you will get some other constant on the right. No. So this capital C will only depend on little c. The k dependence I have explicitly wrote to be k square and then this k log n. It's not on the last, and we also don't care. So if you recall, like we are interested in k about square root n, right? And for k about square root n, this k square becomes n. Yeah. So you will not get exponential rates on the last one, and we are right now interested only not in the last one, but something like n minus square root n or something like that. Yeah. Okay, so because we can extend it to any fixed matrix G plus A, what exactly do we have? We have G plus this more complicated thing. The good thing is C is fixed from the problem, AI are fixed and BI are fixed, but the troublesome part is that there is this thing that depends on UU transpose which we don't have any control over in the additive matrix that we are adding. Because we don't have any control over this, we end up having to do an epsilon net on. So if you consider this entire coefficient to be a lambda I, then we do an epsilon net over this m dimensional space because there are m of these, one for each constraint. And when you do an epsilon net and apply this the concentration inequality for each value of lambda I, when you take a union bound, you get an additional factor of 1 over epsilon to the m, right? Because you are doing an epsilon net in the m dimensional space. So you take say unit ball in the m dimensional space and find a set of points so that any other point has a point in this which is close, whose distance is at most epsilon. Sorry? I did not understand. Can you repeat what you said? Yeah. Yeah. No, the threshold will also slightly change. Yeah. 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 So when you do epsilon net and then you extend it to the entire space, so it will also change the threshold. Yeah. Yeah. So in an m dimensional space, the size of an epsilon net will be about 1 over epsilon to the m, right? And then because you are taking union bound, you'll multiply both of these, and this e to the minus k square should still dominate, should be able to kill this 1 over epsilon to the m, and that's where you get k square to be greater than or equal to m log 1 over epsilon, or k greater than or equal to square root of m log 1 over epsilon. Okay. So there are a few more technical issues in actually doing this fully, because we can do epsilon nets only on finite domains, compact sets. We cannot do an epsilon net in the entire space, and a priori it's not clear that these lambda i's which we are using to denote this ai uu transpose minus bi, these need not even be bounded. These could go arbitrarily large, and then we cannot really do epsilon net over the entire space. But we need to do a little more work to show that ai uu transpose minus bi does not really grow too large for especially at second order stationary points, because we are looking at this only at approximate second order stationary points. So if you restrict yourself to approximate second order stationary points, you first have to show that ai uu transpose minus bi does not become too large. So it's sufficient to do an epsilon net in a compact space. However, so for that, as I mentioned, so we need to show